The topic that we are going to discuss today is a very, very, very important topic, and that is first law of thermodynamics. It's very important, actually, not just for thermodynamics, but all the applications of thermodynamics, and even in general, wherever you will, relate any concept from heat transfer or thermal engineering, first law will be useful. It will be applicable somehow there. And anyway, you may have heard that the energy of the universe is conserved, right? That is basically the first law of thermodynamics. Okay, it is energy conservation, that the energy is conserved. So, this law, first law of thermodynamics, is a universal law. Okay, it's a physical law, and it's applied everywhere. It's applied everywhere. So it's very important. We are going to see the applications of it and how it is useful, how it is applied in thermodynamics. Okay, so should we go ahead? Can we start? I think we have enough people in the class, and we can go ahead now. Yes. Okay. Now, so already you people know we are going to discuss first law of thermodynamics, right? And you I have already discussed my introduction in last class. Let's directly go to the topic. Now, before we go ahead, to understand what is the first law of thermodynamics, there are few things that is good to know. And the thing is that we have discussed process. What is process? When the state of the system is changed from one equilibrium state to another equilibrium state, that is a process, right? So there can be different types of processes in thermodynamics. Okay. So what are the different processes? What are the different processes? They are the different processes in thermodynamics. Anyone? What are the different processes? Quickly, what can you come up with if you remember anything? Yes, very nice. Isochoric, which is also called as constant volume. Okay. Second, we have isochoric, isobaric, which is also called as constant pressure. Then we have isothermal, temperature constant. Then we have adiabatic. Yes, here it simply means that heat transfer is not happening. Heat transfer is zero. Okay. And last is polytropic. Polytropic. Now, polytropic is the most general process. PVN is equals to constant. Now, basically, it is the most generalized form of process. Most generalized form of process. So basically, you can express all your processes in terms of polytropic process. The general equation of any process is basically PVN is equals to constant. And what it is telling you, how pressure and volume is related. So basically, if I draw a PV diagram, and I can draw any process from 1 to 2. Okay, so let's say I am drawing this process. So if I am able to find out the slope of this line, and it is what is happening here, pressure and volume is continuously changing. So basically there is a relationship between pressure and volume to show this process. Okay, if I am able to find out what is the relationship between pressure and volume, I can define my own process. I don't require these process. If I As long as I know, or as long as I am able to figure out the relationship between pressure and volume, I can determine my own process as well. Okay. So people are writing so many things here. Isentropic, quasi-static, yes, okay, but they are not the real processes. Okay, quasi-static is basically an approximation of a real process. Okay, so basically a real process is whatever is happening around us. But if you assume that that real process is happening in a very 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 slow manner, okay, then it is a quasi static. So it's an approximation, so that we will, because for a real process it's very difficult to analyze the system. Now what you do, you assume that that real process is happening in a very slow manner, that is quasi static. Now, what is isentropic? Basically, reversible. We have adiabatic and reversible adiabatic process is isentropic. Okay. So those are not real processes. These are real processes. These are real processes. Reversible adiabatic process is what? Isentropic process. We will see that as well later on. Okay. So basically, we have these five processes, or you can say we have these four processes, and this is the most general form of process. Okay. Chalo. So let's discuss them one by one. First is isochoric process. First is isochoric. Now, how does this isochoric process look like? That means a constant volume. It simply means constant volume. So whatever is happening in the system, for example, you see, you take a cylinder like this with a rigid boundary, and it has some gas. It has some rigid boundary, and it has some gas. Okay. Now it has some gas, let us say at P1, volume is V1, and temperature is T1. Okay. Now what you are doing, you are giving some heat to it. Now this heat is going to affect the properties of the system. So because the look, volume is remain same. Volume is not going to change because volume is fixed. So volume will remain V1 itself. But the pressure will increase P2 and temperature will increase T2. Okay. So the properties are changing. So you, if I have to draw a pressure volume diagram here, so you see pressure volume. Now I know that volume is same. I know that volume is same. So what kind of line I can draw on this PV diagram that will have a constant volume? Can anyone tell me? How can I show a constant volume? Vertical line, yes. So you see, I am going from point, I am going between these point 1 and 2. I don't know in which direction, but you see, if I am traveling in on this line, my volume is fixed. So V1 is equals to V2 is equals to V. Initial volume, final volume is equals to, or let me write it in a way that, where is eraser? Okay. Yeah. So I can write V initial is equals to V final is equals to V1. Okay, volume. Now volume is constant. I am giving heat. So what is happening? Pressure is increasing. So that means I am going in this direction. So you see, my pressure is increased from P1 to P2 and my volume is constant. So you can show a constant volume process by this curve. It is very important how to show each and every curve on the PV diagram. Okay, so this is how you will show up constant volume process on a PV diagram. Now, as I said, in this process, it is also called as isometric process. It's also called as it's very rarely used, this term, but even if I mean it's very very rarely used, but still you must know. Okay, so volume is constant. Now if I need to draw ideal define ideal gas equation for this process. So first of all, what is ideal gas equation? PV is equals to MRT. Now, by I can write MR by V into T. Now, M and R is already constant. Okay, mass is constant. Mass is not changing. R is also if it is air, it is it is same. Okay, for a specific gas, it is defined. And in this particular case, volume is also constant. So this everything, this whole thing is constant. So I can write P by T is equals to constant. So this is my ideal gas equation for constant pressure process. So I can write like P1 by T1 is equals to P2 by T2, or I can write P1 by P2 is equals to T1 by T2. Very important to understand here is that all these equation can only be used for isochoric process only. Very, very important. Don't just go and randomly apply anywhere. It can only be used for a constant volume or isochoric process. Okay. So let me write it here. Very important note. Constant volume process is shown as vertical line parallel to pressure axis on PV diagram. On PV diagram. Is it clear? Okay. Then the next process we have is constant pressure process. It is also called as isoplastic process. Isoplastic. Now, how does this process look like? You see, now I will take a piston cylinder arrangement like this. Earlier it was fixed. This time the piston can move. This time the piston can move. So my initial pressure is P1, initial volume is V1, and initial temperature is T1. Now what am I doing? I am giving it some heat. So when I am giving it some heat, what is going to happen? You see, this heat is going to try to increase the temperature and pressure. Increase the temperature and pressure. Now, this piston. So, for example, as this pressure is it will slightly rise. For example, initial pressure is P1 is equals to 100 kilopascal. Now, I am continuously giving heat. So as soon as this pressure will increase to 102 kilopascal, the piston will move up and it will bring down the pressure as 100 kilopascal again. I am just giving you it an example. It is I mean these figures are not accurate. Okay, it will not actually go to 102. Basically, it will happen very minutely. So as the pressure is slightly rising, the piston will move up and the pressure will again decrease. Again, the pressure will increase, piston will move up and the pressure will remain constant, remain same. Okay. So what will happen is if you keep giving heat, the piston will move up such a way that this pressure will remain as same as P1. Now piston is moving. So when piston is moving, of course, volume will change and my temperature will also change. My temperature will also change. So this type of process will be a constant pressure process. Now, how can I show this on a PV diagram? Anyone? How can I show this on a PV diagram? My my pressure is on y axis. and I am saying my pressure will remain same. So for any process pressure to remain same, that means I can go in horizontal direction from 1 to 2. So if I am traveling on this x from 1 to 2, that means my pressure is not changing. So here I can say my P initial is equals to P final is equals to P1. But, but you see, your volume is increasing. So initially your volume was V1. Now you have reached at 2 position and your volume is increased to V2. So this is your constant pressure process. So can I write here that on PV diagram, constant pressure process is shown by a horizontal line parallel to volume axis. Okay. Now how can I, so here my pressure is constant. How can I define the ideal gas equation? So always start with the basic equation. What is the basic equation? PV is equals to MRT. Now volume is equals to MRP by T. Now this time this is constant. So here V by T is equals to constant. So this is basically your ideal gas equation. Now you can also write this as V1 by T1 is equals to V2 by T2, or you can write it as V1 by V2 is equals to T1 by T2. Every point that I have written here has some importance, and you can use that later on for any in any numericals. Now Amit is asking how pressure will remain constant. I have just explained you what is happening here is, look, initial pressure is P1 but the piston is flexible. Piston can move, there is no restriction. You see, if you apply some restriction here, so piston is not going to move. So what will happen? Pressure will increase, but because piston is not moving, so volume will remain same. But in my particular case, I am not using these. So piston can move up or down freely. Piston can move up and down freely. Now what is happening? You see, I am giving heat. I am giving this heat and the initial pressure is P1. Now when I am giving this heat, the molecules inside, gas molecules, are going to feel the pressure. So basically, what is pressure? When these molecules collide to one another, so basically pressure is the average collision movement that happens. Okay, pressure is the resultant of V2 by T2 correction. No, I didn't understand what you want to say. V2. Oh, sorry. Yes, sorry. Yes, that is correct. Okay. Now, what is going to happen here is, basically it is, what is pressure? Pressure happens because the molecules basically strike the walls and they apply certain kind of pressure. Okay. Now, when you start giving heat, so the pressure will increase inside the cylinder. It will increase, yes, but as soon as it will increase slightly. For example, initially it was 100 kilopascal. When it will go to 102 kilopascal, so the piston will move up. Why it will move up? It will move up against the pressure increase so that it can keep the pressure constant. Okay, so again this pressure will come down to 100 kilopascal. Okay, so again, don't take these figures as literal numbers. What I am trying to say is, as soon as you are giving heat, the pressure will try to increase, but In response to that pressure increase, the piston will rise up. And when the piston will rise up, the volume will increase, but the pressure will remain same. If we add heat to the system, it will change volume, pressure, temperature, but how we manage the pressure remains constant. That's what I am trying to tell you. No, that look, in this case, in the last case, it basically depends on what is your system. In this last case, we have managed our system in such a way that the volume is constant. So if volume is constant, pressure and temperature, they are inversely proportional to each other. Okay, they are inversely proportional to each other. So you see, pressure will increase, and to remain this ratio as constant, temperature must also increase. Okay, so basically, it is the behavior of the gas, how pressure, volume, and temperature are related in a gas. So I have chosen my system. Now in this system, volume is constant. Okay, in this particular system, my volume is constant. Now pressure, volume, and temperature are going to react based upon this equation. Now volume is constant, so volume can't do anything, but pressure and temperature are related in such a way in this particular case. So you see, always pressure by temperature will remain constant. So if there is a, because of this heat, if there is a rise in pressure, there will also be rise in temperature to keep this ratio as constant. Simple. Now in the next case, here, how volume and temperature are constant. In this system, again, I have chosen this system in such a way that my pressure is constant. Now, again, I will tell you one thing. Your system can be in such a way that pressure, temperature, volume, everything thing is changing. So, what will be that pressure? It will be, what will be that process? It will be a polytropic process. No, that is not true. I'll tell you, Amit. Just wait for 1 second. So, Abhishek, again, to answer your question, uh, pressure, volume, and temperature will change based upon the process that you are using, and the process that you are using will basically define the system, what kind of system you need. So in this particular system, my pressure remains constant. If my pressure remains constant, this is how my volume and temperature are going to react. So the volume by temperature is constant. So whatever heat you are giving, pressure will remain constant. Yes, volume will increase. You see, volume is increasing, piston is going up, volume is increasing. Now volume is also increasing. Temperature also must increase to keep this ratio as constant. Okay. So in this particular case, if I draw a TS diagram as well, temperature will also be increasing. Okay. Now coming to Amit questions, it's not necessary heat will go outside. You can see, you can do this. You can insulate this. Okay. So what is happening? Only pressure remains constant. By piston is moving, and it is the piston movement is compensating for the pressure. It is not happening due to the heat is that is going out. Okay. Chalo, let's move ahead. Next is isothermal. Next is isothermal. Now, what is isothermal? Isothermal is basically when temperature remains constant. When temperature remains constant. Okay. Now, how temperature will remain constant? Let us see. Again, let me draw a system such that the only restriction is of temperature. Only restriction is of the temperature. So initial pressure is P1, volume is V1, temperature is T1. Okay. Now I am giving some heat. I am giving some heat. Q. Okay. Now whatever heat I am giving, that heat is basically, some heat is radiating out from here, some heat is radiating out from here, some heat is radiating out from here. in such a way that the temperature is not changing. Temperature will remain same. Only pressure and volume is changing. Only pressure and volume is changing. Okay, so this is basically, it will increase to P2 and it will change to V2 and it will remain as T1. Temperature will remain same. Okay, so if I need to draw ideal gas equation, if I need to define an ideal gas equation, how can I draw? How can I define? Always start with the basic equation. PV is equals to MRT. PV is equals to MRT. Now you see, this time, this whole thing is constant. Earlier we have to move pressure or volume, but this time it is constant. So I can say now PV is equals to constant. PV is equals to constant. Okay. So this is one of the equation that we can use. Now we can use P1 V1 is equals to P2 V2, or I can write P1 by P2 is equals to V2 by V1. Now you see here P and V, they are going to change in a opposite direction. So you see the product of pressure and volume must remain constant. So due to this heat that you are giving, if the pressure is increasing, then volume must decrease to keep the product as constant. Okay, so in an isothermal process, pressure and volume will change in the opposite direction. Okay. Now, what is these heat additions and rejections we do reversibly or irreversibly? Look, you always assume that you are doing reversibly, but I mean, it's always an irreversible process. We never do a reversible process. Okay. But for analysis, we assume that we are doing it reversibly, or more accurate answer, if you want, we do it quasi statically. Okay, all the process that happens, heat addition, heat rejection, okay, everything happens quasi. You very slowly you give heat, okay, or very slowly you allow the system to move. Okay, so this is your ideal gas equation for constant temperature process. Now, how do you draw this? How do you draw? So this is, anyone? Yes, very nice. That is a rectangular hyperbola. Okay, so you show it like it is this. It is rectangular hyperbola. If this is my P1 and this is my V1, so you see, let me go from 1 to 2. So if I am going to this, you see my pressure is decreasing P2, but my volume is increasing. Okay, so they are basically inversely proportional, you can say. Irreversible process, we can also achieve isothermal. No, you cannot achieve. Okay, in fact, isothermal process you can never achieve. Okay, that is the one process that is not possible in any way. In fact, you will see that in Carnot cycle also, that isothermal processes are not possible. Okay, somehow you can get a isobaric process, somehow you can get a constant volume process, somehow you can get a adiabatic process also, but isothermal, not possible. Okay, chalo. So this is, and this is basically, the shape is rectangular hyperbola. Hyperbola. Okay, so next process is adiabatic process. Now, adiabatic process is simply defined that a process that does not allow any heat transfer. Very simple. It is a process that does not allow any heat transfer. Okay. So basically, what kind of system? For example, whatever system do you have, whatever system you take, and you insulate it perfectly. You insulate it perfectly. You insulate it like this, everywhere, like this, everything you insulate. So going in, whatever heat is going in, it can never go out. So only change that will happen, it will happen in pressure, volume, and temperature. So this time everything is going to change. Pressure will also change, temperature will also change, and volume will also change. So it is one of the most generalized process. But here one condition is there. What? Heat transfer, no heat interaction. Heat interaction will be zero with the surrounding. Okay, heat interaction will be zero. In fact, let I should not draw this as well. I should not draw this as well, like to be more precise. But I can say once I have given some heat to the system, after that there is no heat transfer. Okay, once I have given, isolated systems have adiabatic process. Yes, you can say that. But again, isolated system is not necessarily a adiabatic process, because isolated, you see, what was the condition for isolated? Isolated is no mass transfer, and what else? Anyone quickly? What else? No energy transfer. Yes. Okay. Now energy transfer can also happen in two ways. What are the two ways? Work transfer and heat transfer. So we are all in adiabatic system. We are only putting a restriction here. We are not saying anything about work transfer or mass transfer. So it's not necessarily the correct definition. So isolated system have adiabatic processes. It's not a very correct definition. Okay. So we are only putting the restriction on heat transfer. There is no heat transfer. There could be work transfer in isolated systems. Oh, there could be a work transfer in adiabatic system. Yes, there could be a mass transfer. Yes, but heat transfer will not happen. Okay. So what is the ideal gas equation? Ideal gas equation is, there's a proof for this as well, but we are not focusing on proof. Maybe late at a later point of time we can do the proof, but right now I'll just give you the equation. This PV gamma is equals to constant. Pressure into volume to the power gamma is equals to constant. Now what is gamma here? Anyone? Gamma, quickly. What is gamma? It is called as adiabatic index, which is also called as Cp by Cv. Yes, no, not gas constant. R is gas constant. Okay, yes, Cp by Cv is, and Cp is what? Is specific heat at constant pressure, and this is specific heat at constant volume. Okay, so now there are few things like Cp is equals to 1.005 kilojoule per kg Kelvin for air. For air, you need to remember these values. And Cv is equals to 0, because in the exam they expect you to remember the values of air. Okay. And R, which is also Cp minus Cv. R is here is gas constant, Punya. So R here is gas constant here. Okay, and this is basically, you can subtract this Cp, Cv from Cp, and it will be 0.287 kilojoule per kg Kelvin. So if you calculate gamma, which is Cp by Cv, is equals to 1.4. Okay, yes, specific gas constant. Okay, And also always remember that Cp is greater than Cv, and therefore gamma is always greater than 0. Gamma is always greater than 0. Okay. So if you want, I don't know if you do you want me to prove this as well from 1 also. Yeah, I mean it is greater than 1, of course. That is actually better. Do you want me to do the derivation now? Anyone? Derivation is not important from exam point of view. Okay, ठीक है, quickly we will do the derivation. Quickly we will do the derivation. So you see, look, there are few things that you know. Actually, I was not trying to derive it because we have not defined the first law. But you see, first law we will see later on. First law of thermodynamics. For closed system, we will define closed system. We will today only we will define this. dq is equals to du plus pdv. Okay, and also first law of thermodynamics for open system. This we define on maybe after 1 or 2 classes. It is dq is equals to dh minus vdp. Okay, now tell me, when I say adiabatic process, it simply means that dq is equals to 0. Simply means that dq is equals to 0. When dq is equals to 0, that means this is 0 and this is 0. So I will get du is equals to minus pdv. And from here you will get dh is equals to v dp. Okay. Now this is general deductions from our first law and second law for adiabatic process. Again, for adiabatic process only. Now we also know one thing: ideal gas dh, or let us say du, is equals to m cv dt, and dh is equals to m cp dt. So let me replace these values by this. Okay, so du is what? Du is minus pdv is equals to mcv dt. Okay, and what is here? Dh is vdp is equals to mcp dt. Okay, now if I just divide these two equations from each other, I can the mass and mass cancel and this. Okay, so now I have, what do I have? I can write dp. If I just rearrange this, I can write dp by p is equals to cp by cv will be gamma and dv by v. So now I can integrate this. So if I integrate this, let me write it here. Ln p is equals to minus gamma. I hope you are all comfortable with this. K is integration constant. Okay, so I hope you are all comfortable with integrations. These are very basic integrations. Okay, and K is integration constant. Now I can say ln p is equals to minus ln v gamma plus k. Ln p plus ln v gamma is equals to k. Ln pv gamma is equals to k. Now, if I take what? If I take exponential on both sides, I can write e to the power ln pv gamma is equals to e to the power k. So this I can remove. It will be e to the p to the power gamma is equals to e to the power k. Now k is an integration constant, and e to the power a constant will also be constant. So I can write constant. Okay. So you have to remember one thing. This equation is only valid Only valid, first of all, for adiabatic process. Why? Because this was the first assumption we took here and started our equation. Second, it is valid for ideal gas. Okay, why? Because these equations are only valid for ideal gas. Okay, so ideal gas. Now also I'll tell you one thing, whatever equations we are defining today, you see these equations, these equations, these equations, people just generally apply them anywhere. Okay, for example, they will give you water in the question and you will just apply it. You cannot apply with water. It is an ideal gas equation. Unless it is a gas, you cannot apply this equation. So make sure that in the question you see air or any gas, or even if say vapor or they say steam, then only you can apply these equations. Then only you can apply these equations. Okay, clear? Okay, now what is next? Next is we have to prove one or two things. I am not saying, one second, I am not saying PV gamma, power gamma is equals to ideal gas equation. I am saying, particularly listen, I am saying PV gamma is equals to constant is the ideal gas equation for adiabatic process. This is what I am saying. I am not saying ideal gas equation is basically PV is equals to MRT. Now you are just modifying your equation for constant volume, constant pressure, constant temperature, adiabatic, and polytropic. Okay, but we started from the ideal gas equation, so we just modified that. Okay. Okay, so now we have to prove one or two more things for adiabatic process. Yes, yes. Should I go ahead? You can get the PPTs later on anyway. Okay. Okay. Now, one more important thing that you will come across is I need to prove something. What I need to prove that for a adiabatic process, T2 by T1, this equation you may have seen so many times. One second. Okay. P1 by P2, P2 by P1, gamma minus 1 by gamma. Have you seen this equation? Have you used this equation? Now you cannot just apply it anywhere. Again, remember you cannot just apply it anywhere. There are few conditions that it needs to satisfy. What? The process must be adiabatic. The process must be reversible. And the working fluid should be a ideal gas basically. It should be gas. Yes, isentropic. Yes, very nice. So reversible adiabatic is isentropic. Okay. Reversible adiabatic is isentropic. Now let me prove this for you quickly. Okay. So basically for reversible adiabatic process, I have just defined that PV gamma is equals to constant. And what is my general equation, ideal gas equation? PV is equals to MRT. So let me take volume out from here, MRT by P. And let me substitute my volume here. So I can write pressure MRT by P gamma is equals to constant. Yes. Now, what else I can do? I can write P 1 minus gamma. I can write, yes, 1 minus gamma. Here I have 1. Here I have gamma. And I can write P gamma is equals to constant upon mr gamma. Now this is a constant also. This is a constant. So this everything is basically a constant. So P1 minus gamma, P gamma is equals to constant. Okay. So I can write P1 1 minus gamma, P1 gamma is equals to P2 1 minus gamma, T2 gamma. Okay. So I can write T2 by T1 gamma is equals to P1 by P2 1 minus gamma. Okay, I can slightly modify it and I can write T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma. And this is my equation, which is again, how did I start? I start with reversible adiabatic process and ideal gas only. So it is only valid in this particular condition. It is only valid in this particular condition. Okay, so this is the relationship between temperature and pressure. Now there is one more relationship. There is one more relationship. What is that? That is, Abhishek is asking, is ideal gas equation for adiabatic? Then why are we using in case of adiabatic? Abhishek, you look, I'll tell you one thing. Do not just relax for some time. Do not overcomplicate things. Do not try to remember the things as it is. You see, look, PV is equals to MRT is valid everywhere, irrespective of it is constant pressure, constant volume, adiabatic, polytropic, isothermal. Whatever it is, you can apply this equation anywhere. If you do not remember PV gamma is equals to constant, you can start with this equation for adiabatic, no problem. You do whatever you want. They are saying adiabatic, you can apply with this, start with this equation and do whatever you want. Okay. Now we have applied few assumptions and we have derived PV gamma is equals to constant. So this is the general equation. It is valid everywhere. It is only valid for adiabatic. Now you are saying, why did we use PV is equals to MRT? You see, here we have pressure, here we have volume. But I wanted a relationship between pressure and temperature. Okay, so how do I get this relationship? I can take out temperature and pressure from, I can take out volume from here, substitute it here, and I will get a relationship between pressure and temperature based upon this equation. Okay, so this is applied anywhere. This is only for adiabatic. Now this relationship, you see, again I'll tell you, adiabatic. The parent equation is PV is equals to MRT applied anywhere. Now for adiabatic, you have defined the relationship between pressure and volume like this. PV gamma is equals to constant. You have find out a relationship between temperature and pressure P2 by P1 as gamma minus 1 by gamma. Okay. So now you have a relationship between Pressure and volume, you have a relationship between pressure and volume. For adiabatic, you have a relationship between pressure and temperature. So what is left? Now what is left? Now you want one more relationship. Look, we can work without that as well, no problem. But to simplify these equations, you see when you see a question, you can start with this as well, then you can come down to this, then you can come down to this, but it will take some time. So we in our preparation phase we try to simplify things. Okay. So it is the process of simplifying. Now we have pressure and volume, we have pressure and temperature. Can you say we can find out the relationship between temperature and volume as well? Yes, temperature and volume as well. So that relationship is T2 by T1 is equals to V1 by V2 gamma minus 1. Now you will say, sir, how did it come? It's simple. We have defined this equation, right? We have defined this. Similarly, we'll do for that equation. What we will do? By we will do for reversible adiabatic process. What do we have? PV gamma is equals to constant. Then general equation, what is general equation? Ideal gas equation. PV is equals to MRT. Now I want a relationship between volume and temperature. So what will I take out? I will take out pressure. Pressure is equals to MRT by volume, and I will substitute here. So it is MRT by volume. Volume gamma is equals to constant. So this is T volume gamma minus 1 or T1 is equals to constant. Okay. So it is T1 V1 gamma minus 1 is equals to T2 V2 gamma minus 1. So basically T2 by T1 is equals to V1 by V2 gamma minus 1. Okay. So this is the relationship between temperature and pressure. This is what we have defined here. Clear? Look, I know that there are so many formulas in thermodynamics, but if you solve questions, you will be okay. You cannot escape from formulas. I mean, there's no other way. Okay. Now, polytropic process is basically same. It is same. It is same as adiabatic process, but it allows heat transfer. It has no restriction to heat transfer. Okay. So its ideal gas equation. When I say ideal gas equation, I mean particularly for this process. Particularly for this process. Yeah. Okay. This one, this one. Okay. Okay. So when I say ideal gas equation, I do not mean I am changing my ideal gas equation. I am saying ideal gas equation for this particular process. So it is PVN is equals to constant. Now what is N here? What is N here? N is basically polytropic index. N is polytropic index, and the value of n varies from 1 to gamma, 1 to gamma. Okay, so you have to remember this. You see, isothermal process, we have PV1 is equals to constant. Then we have polytropic process where I can say PVN is equals to constant. Then I can say adiabatic, PV gamma is equals to constant. So this, let us say this is a this is a variable. So here k is equals to 1, here k is equals to n, here k is equals to gamma. So this value of n lies between 1 and gamma. Okay. So it is also shown by this PV ga n is equals to constant. Okay, clear? Yes, no. All the derivations that we did in adiabatic will follow here, but instead of adiabatic, but allow his heat transfer. Adiabatic, basically it follows the equation, it follows the same pattern as adiabatic. Okay, but in this process it will allow heat transfer. So there we have taken, you see, all the equations, for example, pvn, and then t2 by t1 is equals to p2 by p1. There was gamma minus 1, but here it will be n minus 1 by n. Similarly, T2 by T1, V1 by V2. What was that? Gamma minus 1 or okay, yeah, it is n minus 1. So basically, all the equations will be valid here, but instead of gamma, we will have n. So it is not applying that restriction on heat transfer. It is allowing the heat transfer. Okay. You see, in adiabatic process, what was happening is my pressure is also changing, my temperature is also changing, my volume is also changing. But I have applied a restriction of q is equals to 0. Okay. So it is kind of a general process. It is kind of a general process, but with one restriction. But if I give you one more process in which pressure, temperature, and volume is changing, and it is also, there is no restriction of heat transfer. So basically it is the most generalized process without any restriction. Because you see, from all other processes, for example, constant pressure, pressure is constant, second volume is constant, temperature is constant. So we have restrictions everywhere. In this, everything is changing, but again we have one more restriction. But this is basically the most generalized process. Okay. Chalo, let's move ahead. Now we have to define slope of different ice thermodynamic process on PV diagram. Okay. So as I said, look, every equation, we will see that every equation that we have defined, it can be determined in terms of PV to the power k is equals to constant. PV to the power k is equals to constant. So this is the most general equation. This is the most general equation. Now, if I differentiate this equation, it will be dp vk plus, now this is pressure is constant, k vk minus 1 dv is equals to 0. So now what can I do? dp vk is equals to minus pk vk minus 1 dv. dp by dv is equals to minus k p vk vk minus 1 is equals to minus k p v minus 1. So basically minus k p by v. Okay. So can I say dp by dv is equals to k minus p by v. But you tell me what is dp by dv? If I if I give you a diagram, this is x, this is y. So can you tell me what is dy by dx? Anyone? Quickly. Yes, it is slope. So similarly, if I am giving you pressure by volume, so what is dp? What is dp by dv? dp by dv. Wait, Harsh, I'll answer your question. Just wait for 1 second. Okay. Yeah. So what is dp by dv? It is again slope. So if I am drawing any type, any process here, if I am drawing any process here, the change dp by dv will tell you the slope. It will tell you the slope. So based upon this, I can derive this slope for each and every process. I can derive this slope, the value of k for each and every, the value of k for each and every process. Okay, that is what we are going to do. So k is basically the constant on which, let me write it for you. dp by dv is basically the slope of, or slope on, uh, slope of curve, let us say slope of curve on what? On pressure volume diagram. Okay, and what is k? K is basically a constant on which slope of every process depends. Okay, so hers, just wait for 5 minutes. Let me complete this. So you will, I hope that you will eventually get the answer without me explaining it. Okay. So I started with this, and I have found out that dp by dv I can define in such a way that if I find a slope, if I find a slope, then what is this k? So k is basically this k is this. So it is a constant on which the slope will depend, on which the slope will depend. Okay. So let us see each and every process. Okay. So this is my general equation for each and every process, and this is my slope. This is my slope. So you tell me one thing. If I have constant pressure process, constant pressure. So let me draw it here. How do I draw constant pressure process? How do I draw constant pressure process? On a PV diagram. Constant pressure. No, that is not slope infinite. Pressure. Yes, horizontal. Okay. Just constant horizontal line, Harsh, not constant line. Okay. Horizontal or vertical line. So basically here dp is equals to 0. So if I substitute in this equation, that means 0 upon dv, change in pressure, is equals to k minus p by v. So here slope is what? Here k will be equal to 0. So you see, who was saying slope? No, slope infinite was not there. Slope is 0. Slope is 0 for constant pressure. Okay. So k will be 0. K will be 0. Okay. Now, what about isochoric? Isochoric. So isochoric is drawn like this. Isochoric is drawn like this, and here dv is equals to 0. Let me not write here dv is equals to 0. Let me write, in fact, okay, just 1 second. Let me draw it a little bigger so that everything I can explain here. Okay, so I have drawn this curve where k is equals to 0. Now isochoric, can I draw it like this? Yes. And what do I know? That dV is equals to 0. So I can write dP by 0 is equals to K minus P by V. Now anything divided by 0 is what? Infinite. Yes. So here K is equals to infinite. So it is constant volume process. K is equals to infinite. Okay. Next is isothermal. Next is isothermal process, and we already know. Look, this is my general equation, and this is equation what I have defined. So if I compare these two equations, so can I say k is equals to 1? Can I say k is equals to 1? Yes. Okay. Now again, this is my general equation. This is my adiabatic equation. By comparing this, can I say k is equals to gamma or k is equals to 1.4 for air? Yes. Now again, this is general equation, this is polytropic process. Can I say K is equals to N? And this N lies between 1 to 1.4. Okay. Now, tell me one thing. Look, can you see this? Here K is equals to 0. Here K is equals to infinite. So can you say that K is increasing in this direction? Can you say this? But it is increasing from 0 to infinite? Yes. Here it is 0, here it is infinite, so it is increasing in this direction, you can say, or yes or no. Are you able to understand what I am trying to say? Do you agree with me? Okay. So again, here k is equals to 0, here k is equals to infinite. Now I have to draw a line that k is equals to 1, k is equals to 1.4, and something between 1 and 1.4. So you see, by I have 1, so 1 will be close to 0 here somewhere. You see, now again I'll tell you one thing. I have to draw three lines. The smallest one is isothermal. The K, the smallest value of K is isothermal. The largest value of K is adiabatic. And the intermediate value is polytropic. So you see, isothermal will be drawn somewhere near K is equals to 0 like this. Here also near to 0, here also near to 0. Okay. Then adiabatic will be drawn very near to k is equals to infinite, like this. So k is equals to gamma. Blue one is k is equals to 1. Okay. And how about polytropic process? Anyone, any idea? How do I draw polytropic process? Anyone? By this is k is equals to 1, this is k is equals to gamma. The value of n lies between 1 and gamma. So how should I draw this line? Between, yes, between k. So I will draw somewhere here. Somewhere here. Okay. So this is k is equals to n. So this is how you draw all your curves on PV diagram. Now, why I was saying again, Harsh asked this question, why I was saying this is a general equation. So you see, by using the value of k, you can define all your equations, all your processes by this equation. So I for isobaric process, I can say PV0 is equals to constant. Okay, so this will be 1. So I can say pressure is equals to constant. Okay. Isochoric, PV infinite is equals to constant. Okay. So we have to multiply it by multiply and divide by 0, and eventually you will get volume is equals to constant. Okay. Then this is PV1 is equals to constant. This is PV gamma is equals to constant. And this is PVN is equals to constant. So basically, this is the equation that we have defined to identify each and every process on a PV diagram. Ki how can I draw each and every process on PV diagram? This is why this is the equation that we have come up. PV is equals to MRT is the most identified. I mean, this is how it is defined. But what we do is we try to mold, we try to modify that equation based upon our usage, our convenience, or how do we want that equation, how do we want to use that equation. So it is the one way to determine all the processes that helps us to identify them on the PV diagram. You see, by using the value of K, I have defined all the processes. By using the value of K, I have drawn all the processes on PV diagram. This is the use of it. Okay, clear? So again, Harsh, PV is equals to MRT is the law that is defined. Now, what we do based upon our convenience or our usage, we try to modify that equations. That is what we are doing from the beginning only. Okay, we modified our ideal gas equation for constant pressure. We modified our ideal gas equation for constant volume. We modified it for isothermal, and again and again and again. So we just do it for convenience. That's all. We wanted to show all the processes on the PV diagram. That is why we defined a general equation so that we can come up with a slope to show it on PV diagram. Clear, everyone? Yes or no? We are really running late on time. So as I said, look, this was my general equation, right? dP by dV is equals to K minus P by V. So for adiabatic process, K is equals to gamma. For isothermal, K is equals to 1. Okay. So basically, and gamma is equals to 1.4. So what can you say? If you compare the slope of isothermal and adiabatic, so you can say that the slope of adiabatic curve is gamma times of slope of isothermal curve. So basically the slope of adiabatic curve is greater than the slope of adiabatic curve. Let me give you one example, PV diagram. This is my process 1, this is my process 2. Can anyone tell me which process is adiabatic, which is isothermal? Write 1 dash whatever you think, and 2 dash whatever you think. What process is this? One is adiabatic. Anyone who has a different opinion? Okay, let me give you one more thing. Yes, 2 is isothermal. Now tell me which one is adiabatic, which one is isothermal? One or two? One is isothermal, two is adiabatic, one is isothermal. Anyone who contradicts with this? One is isothermal, two it very nice, very nice. So always see, you see wherever you draw this line and see which one is close to y-axis. So this one is close to y-axis, this is a greater slope. So this is adiabatic. This is close to x-axis, it has lesser slope. This is isothermal. Okay, very nice. Chalo, let's. So this conclusion is this. And again, this equation we have defined, very important equation in your propulsions, in your power plant, in your everything. You are going to use that infinite number of times, this equation. Wherever propulsion you will deal with, wherever gas expanding, you see expansion or compression, wherever you will see, it will be isentropic. Wherever you again, I will tell you one term. Wherever you will be dealing with compressors and turbine, you will see this term, isentropic compression or expansion. As soon as you see isentropic, that means reversible adiabatic. And you are free to use this equation, and you are going to use this infinite number of times when you solve the questions. Okay, chalo. So, okay, very nice. Now let us come to the work transfer. Let us come to work transfer. So, what is work transfer? The work transfer is basically the ability to move, ability to raise weights. Okay, ability to, just one second. Okay, so basically, if I say thermodynamic work, the definition is basically work is said to be done. Work is said to be done by the system whose sole effect on things external to the system can be equated to raising of weights. Don't worry about the definition. Raising of weights. What does it mean? See, let's say you are standing here. You are standing here. Okay. And I have tied a rope with you, and it's some weight is hanging here. Okay. Now, when you move in this direction and you move from one point to two, what will happen? This weight will rise up, and this is your system. Okay, this is your system here. So basically, whatever you are doing inside the system, eventually it is causing the raising of weights. So you can say a work has been done. Okay, I'll give you one more example. Let's say you have a battery here, and with this battery you have connected an electric motor. Electric motor you have connected. Okay, and this motor is basically connected to a pulley. Okay, it is connected to a pulley, and pulley is connected to a weight. Okay, now when you switch on this battery, it is going to rotate, and this pulley is going, I mean this shaft is going to rotate, and this weight will be rising up. So basically this system that you have, this battery system, whatever you have, it can be equated to raising of weight. Now again, this, it's not necessary that the weight is actually rising, but the thing is somehow you can connect your system in such a way that that you can raise a weight. For example, you are standing here, you have a stone here. Okay, you have a stone here. Okay, and you just push it a little bit, and it is coming down. So can you tell me, is this stone is doing a work? Yes or no? Can you say it is equate? Why not? Anyone who can say yes, it is doing some work? Why are you saying no? I want reasoning behind it. Why someone is saying no? Or if you are saying yes, why are you saying yes? Okay, some people are typing so much, so many things. Okay, let me tell you. Yes, it can be equated. Look, you cannot see the rope here, right? You cannot see the rope here. But just imagine if you tie a rope here. Just imagine. Just tie a rope here and leave that weight here. So when it is coming down, it will take that rope with it, and this weight will come up. Okay. So yes, it can be equated to raising of weights. Of course, it can be equated to raising of weights. So whatever you are doing, maybe it is not raising weight, but if you can imagine a system that you can somehow raise a weight from it, you can say that work is getting done. Okay. Again, I am going to tell you, it is not necessary that you are actually raising a weight, but if you can imagine a system that you can attach with that thing so that it can raise some weight, so you can say that the work is getting done. Okay. So now how do you calculate work? So let us say you have a piston cylinder arrangement. Again, very important point, we are talking about closed system work. We are talking about closed system work. Okay. So what is closed system? What is closed system? Quickly, someone tell me what is closed system. Yes, no mass transfer. Okay. So what do we have? Let us say we have some gas here. Okay. And it is applying, let us say, pressure P1 on this piston. Yes, only energy transfer. Okay. It is applying pressure P1 and volume is V1. Volume is V1. So the initial thermodynamic equilibrium is P1 and V1. Now what are we doing? We are giving some heat. We are giving some heat to this. So what is going to happen? This piston is going to move and it will come here. It will come here. The piston will come here. Now, if the piston has come here, then of course its pressure and volume may have changed. So final pressure is P2 and final volume is V2. Final pressure is P2 and final volume is V2. Okay. But you see, from the point, look, at a certain time it was P1 and V1. And after, let's say, 5 minutes or 10 minutes, it has reached to P2 and V2. But it may have taken some time, right, in between. So, in that particular, at any particular instant, at any particular time, whatever pressure and volume was there, let us assume it was P and V. Again, I am telling you, it is an intermediate position. At any given instant, at any given instant, the pressure of the whole system was P and the volume was V. Okay. So, what is work? Anyone, what is work? How have you studied work in your 11th and 12th? Work is equals to force into distance or displacement, right? Force into displacement. So what is the displacement that it has done? It has done this displacement x. It has done this displacement x. Okay. So when I say ki at a particular is f into dr. Yes, dr is basically the change in the uh, change in the distance. Okay, change in position basically. Okay. So at a particular instant, the very small distance, again I am saying at a particular instant, if the distance traveled at a particular instant a very small instant is dx. Okay, so I can write small work is equals to whatever force is applied and whatever distance it has traveled. Now what is force? Force is basically at the intermediate position, whatever the pressure was, and what is the area of this, what is the area of this on which the pressure is applied. Okay, del x. So now if I just integrate this, I can do dw is equals to p dv, p dv. Now let me integrate this and I can write work. So from where 1 to 2, this is also 1 to 2. So 1 to 2 is equals to p dv, p dv. Okay, this is my general equation of work transfer again for a closed system. For a closed system, please remember that this equation is only valid for a closed system. For open system, we will do something else. Okay, so this pressure is basically instantaneous pressure. Instantaneous pressure. Okay, at a given instant, it instantaneous pressure. Okay, so now how can I draw this? How can, so basically what we have, let us say we have, this is my piston cylinder arrangement. Okay, so initially my piston was here and the pressure is P1 and V1. So if you ask me to draw the PV diagram, so initially let us say my pressure was here P1 and my volume was here V1. Now as I have given some heat here, so the last position it has reached is this one. Now the final pressure is P2 and volume is V2. So now I have reached somewhere here, let us say. You see, I know that volume has increased for sure. I know volume has increased for sure. Okay, because I can see that here. I can see that here. So volume is V2 and pressure is P2. Now the question is, how do I connect this? How do I connect this system? How do I connect this? So I will connect it based upon the process that is given to me. I will connect this based upon the process that is given to me. Okay. So if it cannot be a constant volume because I see volume is changing. It cannot be a constant pressure because I see pressure is also changing. So either it can be isothermal or adiabatic or polytropic. Okay. So let me take a general process, polytropic process. So let me connect it like this. Let me connect it like this. Okay, so I have just defined for you that work of closed system is equals to p dv. Okay, now let me take a, at a given instant, very small pressure. Okay, at a given instant I am taking a pressure here, and because of this pressure the change in volume is this dv, very small. Because of that intermediate pressure P, a very small change in volume has occurred. Okay. So this is what this, if I talk about this area, what is this? P into dV. Now if I do this for infinite number of times, if I do again, I'll take an intermediate pressure and I take a change in volume. Again I take a intermediate pressure, again I do this, again I, so basically what I'm trying to find out, I'm trying to find out the area between the curve, the area between the curve. So if I do this infinite number of times from point 1 to point 2, so I will get entire area. So for each of them I have p dash, p double dash dv, p triple dash dv, p4 dv. Okay, and if I add them all up, what will I have? If I add them all, can I say it is PdV? If I am adding them all up, can I say that this area can be shown by integration of PdV? Yes. So this, you see, this is also of area under the curve or PV curve extended on volume axis. Okay. So basically, you see, this is work and this is area. So what can I say? Work closed is equals to PdV and also area under the curve. Area under the curve. It is very important statement. It is very important statement because by using this, I am going to tell you why it is a path function, which I was telling you in the last class. Path function. Okay. So work can be calculated by either integration of PDV, or you can calculate. For example, look, I'll give you this. I'll give you this question. I'll give you this exam. In exam, you will get this. Uh, this is 10 kilopascal, and V1 is equals to 10 meter cube, and V2 is equals to 20 meter cube. Calculate work done by this system. Quickly tell me what is the work done by this system. Quickly tell me what is the work done by this system. Yes, 100. Why? Because you see area under curve. What is this area under curve? 10 into V2 minus V1. Okay. 10 into 20 minus 10. 10 into 10. 100 kilojoule. Okay. Let me give you one more example. P1 is equals to 10 kilopascal, P2 is equals to 5 kilopascal, and V is equals to 10 meter cube. Calculate work closed. Quickly. Abhishek, how is it 50? What is it? It is pressure. PdV. Either you can do it like this as well. Okay. PdV. Now, you see what is dV? dV is 1 to 2. V1 is also 10. V2 is also 10. So dV is equals to 0. That means it will come as 0 anyway. Okay. Also, you can say that the area under the curve is 0. There is no area. There is no area. So work is also, you can say by area wise also, you can say it is 0. Okay. Is it making sense to you? Okay. Now you see in this particular diagram, in the first diagram, if I am going from 1 to 2 by this process, by a process, then my work done is this. If I am going through this process, then work will be this area, this area, this area, this whole area, right? So look, I am going from point 1 to point 2 only, but I have taken a different path. So my work A is not equal to work B. So if you change the path, your area covered under the path will change, and that means work will also change. And that is the reason it is called as path function, because it depends on path. It depends on path. Okay, chalo. So let us draw this for each and every process very quickly. Okay, so sign convention is work done by the system is positive, work done by on the system is negative. Okay, so whenever work, if whatever your system is, if you are doing work, for example in compression, you are giving the system work, you will give electrical power to it. Okay, so if you are giving the work, it is negative. If the system is giving you work in. If the system is giving you work, it is positive. Okay. And units, what are the units? It can be, you see, it is work is equals to PdV. So pressure, it can be Pascal, meter cube. What is Pascal? It is force per unit area. So Newton per meter square into meter cube. So Newton meter, which is basically joule, which is joule. Okay. So units can be joule, it can be kilojoule, megajoule, all these things you can use. Okay. Chalo. Specific work, again, you know, anything divided by mass. Anything divided by mass is specific of that quantity. So small w say we denote this, capital W by mass. So kilojoule is work unit divided by masses. So specific work is designated by kilojoule per kg. Power is rate of doing work. What is rate? Work per unit time. Work per unit time is power. So work per unit time is power. Kilowatt. Okay. So again, it is a transient form of energy. I have told you it is path function and inexact differential. Again, it is a path function, so it is not a property. Work is not a property. And it is a boundary phenomena. Why do we say it is a boundary phenomena? Because it has to cross the boundary. It has to cross the boundary. Otherwise, you cannot say that work has been done. Okay. Now let me define work for all the processes. Let me define the work for all the processes. So we will define closed system work for isochoric, isobaric, isothermal, adiabatic, and polytropic process. Okay. So you see, first is isochoric process. Isochoric process. So general equation, always start with general equation. Always start with general work 1 to 2 is equals to pressure into, this is my general equation. This is my general equation. Now, as you say, I have fixed this. I am not allowing my piston to move anywhere. That means volume will remain constant and dv will be equal to 0. dv will be equal to 0. And I don't think that I need to draw the diagram, but okay. PV, so this is how it will look like. Pressure is changing from 1 to 2, but volume yani ki V1 is equals to V2 is same. Okay. So in this case, dv is equals to volume is equals to constant and dv, which is v2 minus v1, is equals to 0, and therefore when you put this is equals to 0, work done is equals to 0 in isochoric process. In isochoric, so I have given you this example as well. You see this one, this example, this is what, this is isochoric process. Work is how much? 0. Got it? Yes or no? Okay. I'm getting very few replies. As everyone is okay with what we are doing, you look, you have to revise. There is no other. Thermodynamics is very confusing subject. I cannot deny this. I cannot give you any excuse for this. The only solution is to revise. You have to do it at least 3 times. Then only you can say, "Ki, sir, I could not understand." If you haven't revised it 3 times, that means you actually need more efforts. Okay. After that, you will start getting some clarity on the subject. Now, next is isobaric process. Isobaric. So, work is equals to PdV. Now, a lot of people do this mistake every time they take pressure outside. They will write it like this. You cannot do that. Particularly, this is isobaric process. That means constant pressure, constant pressure. That is the reason in this particular case, I can keep my pressure outside the integration. Otherwise, people don't, I mean, a lot of students remain confused. They do not see it is isobaric or not. They just bring the pressure outside. They think P is only one value, there is no dv, pressure is constant, I can take out. No, pressure is the intermediate pressure. Okay, and it is inside integration. Okay, but again, because pressure is constant, let me write it here again. In this, for isobaric process, for constant pressure process, now I can bring my pressure outside the integration, and I can write it like this. Okay, and my volume is changing from V1 to V2, so I can write P V2 minus V1. So this is the case also we have seen just now. Okay, this is my P, this is my V1 V2. We have also solved one question on this. Okay, simple. So also this is the area, and area is also given by this. Okay. Next is isothermal. Isothermal process. So look, now pressure is not constant, so I cannot bring pressure outside. I have to deal with it. So how will I deal? I will go to my ideal gas equation. So ideal gas equation is what? Let me write here. Ideal gas equation is PV is equals to MRT. Okay. Now temperature is constant, so PV is equals to constant. Now pressure is equals to constant by V. Constant by V. So I have to bring this here. Now I can say work is equals to constant dV by V. V12, V2. So W12 is equals to constant ln V2 by V1. Okay, so this is one way of doing it. One way of doing it. This is one formula that you can use anywhere. Second thing, now you see, what do I know? I know, look, P V is equals to constant. So can I say P1 V1 is equals to P2 V2? Can I say V2 by V1 is equals to P1 by P2? Yes. So I can replace this as well. Ln P1 by P2. Sorry, it is P2. Okay. P2. I can also write this. Okay. Also, one more thing. What is this constant? What is this constant? This constant can be either, you see, this constant can be P1 V1 is equals to constant, or you can say P2 V2 is equals to constant, or also this is also constant. MRT1 is also constant. Okay, so you can replace this constant value by any one of them. You can also write P1 V1 ln. Look, I don't need to tell you all this, but I am just simplifying this for you so that anything you can use. I mean, it's very obvious that you can use this, but I am just writing it openly for you. Okay. So now what you can do, you can replace this constant by any of these things. And also all these equations can be written in this form as well. So now, sir, why are you telling all these equations? Basically, you have to use any one of the equation. You don't have to use all the equations. You have to use any one of the equation based upon the data that is given to you in question. Okay. For example, temperature is given to you. So you will use this temperature and volume equation. If they are giving you temperature and pressure, so you will use MRT1 ln P1 by P2. This equation you can use. So basically, depending upon what is given to you in question, you can use any of these equations, whatever I have written. Okay. So this is your isothermal. Very important, these equations, you have to write it down. you have to write it down later on a separate piece of paper so that you can keep revising it. Okay, so that you can keep revising it. Next is adiabatic process. So adiabatic again, I always start with general equation PdV. Okay. Now what is ideal gas equation for adiabatic process? PV gamma is equals to constant. So what is P? Constant upon PV gamma. V gamma, sorry. So I can substitute it here. Can I write constant dV upon V gamma? Constant V minus gamma by dV constant V minus gamma plus 1 minus gamma plus 1 V1 to V2. Okay. So constant, now little bit complication is there, but it's okay. If you try to focus, it will be okay. I'm just substituting the limits here. Minus gamma plus 1 upon 1 minus gamma. Okay. Now you see what is this constant. This constant can be either P1 V1 gamma or P2 V2 gamma. Everything is constant. Okay. So I can multiply this constant inside. I can write P2 V2 gamma, then V2 minus gamma plus 1, minus I will multiply it here as well, but I am writing here P1 V1 gamma, V1 minus gamma plus 1 upon 1 minus gamma. Okay, if you simplify this, you are going to get P2 V2 minus P1 V1 upon 1 minus gamma. Now you see, I know that gamma is greater than 1. So this term will be negative. So instead of using this, why don't I write W122 P1 V1 minus P2 V2 upon gamma minus 1. So this is your work transfer for adiabatic process. Adiabatic process. Okay. Same thing, same equation you can use for polytropic, same equation. Because look, the work 122 is equals to PdV, and ideal gas equation is also same. Ideal gas equation is also same. PV to the power n is equals to constant. So same process you are going to follow, and eventually you will get P1 V1 minus P2 V2. There it was gamma minus 1, here you have n minus 1. Simple. Okay, clear? So just to you know brief here, just summarize here, when you are talking about boundary work, isochoric process, what is work transfer? Quickly tell me, what is work transfer? Isochoric, quickly. Zero, very nice. Isobaric, what is work transfer? Quickly. Yes, P. These formulas should be at on your tips. What is isothermal? Isothermal, let me write P1 V1 ln V2 by V1. Or you can write P1 V1 ln P2 by P1. Or you can write MRT1 ln, anything you can write. Anything you can write. Okay. Polytropic. Polytropic is P1 V1 minus P2 V2 upon n minus 1, and adiabatic is P1 V1 minus P2 V2 upon gamma minus 1. These formulas should be on your tips, otherwise there will be a issue. Okay, otherwise there will be some issue, because so many times, very frequently, you are going to use this. Okay, now let us come to the main topic, which is first law of thermodynamics. I mean, it's a very small derivation, but we were building everything until now for this. Okay, so you have to understand one thing: the energy, that whatever you have, can be classified in terms of stored energy and transit energy. Okay, so stored energy means what? Look, if you have a system and it has some mass, for example, let us say whatever, 10 kg, some mass, 1 kg, 2 kg. So whatever mass it has, this mass can store energy in the form of macroscopic and microscopic. Again, remember, this energy is not going out, it is stored inside the system. Okay, so this energy can be stored in terms of kinetic potential, internal energy, or chemical energy. Now, from thermodynamics point of view, we neglect kinetic energies and potential energy and chemical energies, so we never assume. Okay, we assume chemical energy in chemical engineering. Okay, from our perspective, we only try to focus on internal energy, sometimes kinetic and potential energy as well. Okay, but let us say all three we try to take into account. So again, if you have some mass here, if you have some mass here, this mass will be storing energy in the form of, so stored energy will be internal energy plus kinetic energy plus potential energy. Okay, now the next is transit energy. Transit energy is which will cross the boundary, so there are two types of heat or work. So heat must have to cross the boundary. Okay, so this is heat or work, or you are giving some work and it is going out, your system is giving work. Okay, so this is called as heat and work. So this is basically transit energy, and these are path functions. These energies are path functions, while these energies are point function. These are all properties. Okay, these are point function. Okay, so when I talk about first law of thermodynamics, I said that the system with its surrounding can interact in two ways. First is mass, second is energy. Now, because I am talking about closed system, so for closed system, no mass interaction. No, when we go to open system, we'll talk about it. So no mass interaction. Only energy interaction will happen. Only energy interaction will happen. And energy interaction means between system and surrounding. It will only happen in terms of work and heat. It will only happen in terms of work and heat. Okay. So let us try to draw this picture that I have discussed with you. So let us say that you have this system, and this system has some mass. Okay, so because of that mass, there will be some energy in the system which is called as stored energy in the system, and that will be equal to d internal energy plus change in kinetic energy plus change in potential energy. Okay, now let us assume some heat transfer is also happening. Some heat is coming in q1, maybe some heat is going out as well. Some work transfer is happening, W1, W2. Okay. So If I have to draw the energy conservation equation or the first law of thermodynamics, it simply means that the energy remains conserved. Energy remains conserved. So that means energy in is equals to energy out plus change in energy of the system. Energy stored, energy of the system. This is energy of the system. Storage is whatever is stored in the system. So let's say what is going in. Going in is q1 is going in. What else is going in? W1 is going in. Work is also going in. Okay, what is going out? Q2 is going out. W2 is going out. And what is stored? Du plus change in kinetic energy plus change in potential energy. Now let me bring everything on one side. Q1 minus Q2. Work, let me bring here W1. Okay. So this is what I am assuming as Q in net. Okay. This is what I am assuming Q W out net plus M U2 minus U1 plus M V2 square minus V1 square by 2 plus G mg Z2 minus. I have just elaborated the formula for internal energy, kinetic energy, and potential energy. Okay, so this I can write Q122, this I can write W122, and this whole thing will come with us. So basically, this is your first law of thermodynamics. Let me write it here. Q122 is equals to M U2 minus U1 plus M V2 square minus V1 square by 2 plus MgZ2 minus Z1 plus 122. Now this is your first law of thermodynamics for a closed system. First law of thermodynamics for a closed system. Okay. Now again, I am going to now don't sir. I mean, look, I am going to modify this. This is a general equation. Now I can give you this and I can leave you. Okay, go solve questions. But the other way, the other alternative is I can simplify it in a more useful way. I can make it more convenient based upon what type of questions they are asking in the exam, and what is I will give you a very simplified equation so that you can use it everywhere. Okay. So based, I mean, you can use this, yes, everywhere. But if I give you a more simplified equation, it will be more convenient for you to use that equation based upon the question. Okay. Again, remember that there is no chemical reaction. We have not considered any chemical energy here. So no chemical reaction is happening. No chemical reaction is happening. Okay. So you can use this equation anywhere. Now, next is, okay. Next is that what do I have? Just 1 second. Can I cut it? Uh, previous stylus. Previous, previous. Okay, so this is my equation, and now let me assume something. Why I am assuming? Why I am not? Because most of the time you are going to have these assumptions. Okay, so kinetic and potential energy are negligible. If no data is given in the question, I know this spelling is correct, but I am not bothering it. Okay, I let me write the correct. So basically, most of the times they will not give you any data for kinetic and potential energy. So in that scenario, you can assume that kinetic and potential energy are neglected in this particular case. Okay, so if they are negligible, what you can do, your V2 is almost same as V1 and Z2 is almost same as Z2. So basically those part will get cancelled and you will have M U2 minus U1 plus W12 in kilojoule. Okay, so again, it came after the assumptions. So if no data is given upon kinetic and potential energy, then only you can neglect. If data is given, then you will use the general equation. Simple. Okay. Now this is basically called as first law of thermodynamics for a process. For a process. Okay. Now, so I defined my equation. I have defined my first law of thermodynamics for a process. How do I define that? Q122 is equals to M U2 minus U1 plus W122. Now tell me one thing. Now tell me one thing. What is U? U is a path function or a point function? Quickly tell me. Yes, it is a point function. Point function. Let me write it like this. U2 minus U1 plus 1 to 2. You see, this is capital U, but this is small u, okay? So capital U is equals to mass into small u. U small u. Okay. Okay. So it is a point function. That means it is a property. It is a property. Okay. Now, do we understand? Do we have proved one thing that for a cycle, for a thermodynamic cycle, change in property will be equal to zero? Have we discussed this point or yes or no? Yes or no? Quickly. In the last class, we have discussed this. For a cycle, change in property is equals to zero. Yes, because that only depend, because for a cycle you just come on the same point again. Okay, so for a thermodynamic cycle, if change in property is equals to zero, that means du, which is u2 minus u1, will also be equal to zero. And if I substitute this here in this equation, that means q122 is equals to w122. And very important point here is, this is your first law of thermodynamics for a cycle. For a cycle. So again, don't get confused. Don't ask me these questions. Sir, आप तो you are saying कि this is your first law of thermodynamics. This is your first law of thermodynamics. Look, first law of thermodynamics is basically this: energy conservation equation. But when you apply for a closed system, you will get this equation. You will get this equation. This is for closed system. Now, if you apply your assumptions, what are the assumptions? These assumptions. Then you will get for a process. First law of thermodynamics for a process. And then you can further simplify it for a cycle. Further simplify it for a cycle. So just to show you its applications. Now, let's say you have this PV diagram, and in a particular process you have come from point 1 to point. Now what is this? This is the process, right? In this particular process, what has happened? Let's say let's say you have given some heat. You have given some heat, and this system has given you some work out. Okay, so this is the process. So you are going to apply first law of thermodynamics for a process. And what is that? Q122 is equals to du plus W122. Okay. So let us say I have given you that Q in is equals to 20 kilojoule and this is 10 kilojoule. Can you tell me what is the change in internal energy? Quickly. What is the change in internal energy? It is 10. Yes. Okay. So this is 20 is equals to du plus 10. So du is equals to 20 minus 10. Du is equals to 10 kilojoule. Okay. One more question. Same question. PV 1 to 2 we are going. This time in this process I have removed Q. Q out is equals to 20 kilojoule and I have given some work input is equals to 30 kilojoule. Can you tell me what is the work, what is the change in internal energy? Du, quickly. Okay, let's see. So Q in is equals to du plus Q plus W out. You see, the equation, the way we have defined this equation, Q122 is equals to du plus W122. The way we have defined this equation, this is always Q in net, and this is always work output net. So here heat is going out, so it will be minus 20 du. Here work is going in, so it will be minus 30, not plus 30. So du is equals to minus 20 plus 30 is equals to 10 kilojoule. Okay, so you have to remember these things. You have to always take care of the signs. Now, what about a cycle? So now you see, earlier we were only considering one process, so 1 to 2, 1 to 2. Now I am going from 2 to 3 as well. I am going to 3 to 4 as well. And then from 4, I have reached at point 1, 1 again. So I started from 1, I went to 2, I went to 3, then 4, and then again 1. Now, in this one process, I am giving Q in is equals to 50 kilojoule. Here, Q out, okay, Q 2 to 3 is equals to 10. Q 3 to 4 is equals to 5. And let us say this is in. Q 4 to 1 is 15. Also, work transfer is happening. Work 1 to 2 is equals to 5. And work 3 to 4 is equals to 60. Now, can you tell me what is this work 1 to 4? Can anyone tell me what is 1 to 4? Work 1 to 4? Quickly. Last question, then we will close this. So you see, first of all, this is the cycle. So you will apply first law of thermodynamics for a cycle. Now, what is for a cycle? Q in is equals to W out. W out, but for a cycle. This is for a cycle, okay? So for a cycle, I can say Q122 plus Q223 plus Q324 plus Q421 is equals to W122, W223, W324, W421. Okay. Now Q12 is going in. In means positive 50. 223 going out means negative minus 10. 3 to 4 again going out यानी कि minus 5. 4 to 1 coming in plus 15. Now W1 to 2 coming in यानी कि work given to the system it's negative minus 5. Then 2 to 3 is 0. 3 to 4 is going out yani ki 60 plus 60. And let me assume it is going out. I don't know if it is going out. Let me assume it is going out. So plus W4 to 1. So now can you calculate this quickly? How much is 4 to 1, minus or plus? Okay, 50 minus 10 minus 5 plus 15. So this is 50 is equals to 55 plus W421. So W421 is equals to 50 minus 55, and it is minus 5 kilojoule. How did Vignesh got 105? Did you do something wrong, or we are doing something wrong? Anyway, so basically you see minus is coming. What do you mean by minus? Minus means we assume that it is going out, but basically it is the opposite. It is going in. And how much is going in? 124 is 5 kilojoule is going inside the cycle. Okay, work done on the system. Very nice. Okay, so this is how you can apply the first law of thermodynamics for a process. You see, this is only for a process. This equation will only be applied for a process. This is applied for a cycle. This equation is applied for a cycle. Okay, so I hope it is clear. So this is all for today. We have covered so many things today, so many formulas, so many derivations. I hope that, look, if you don't revise again, it is not going to help you anyway. So please revise and make short notes. Try to write all the formulas all together so that you can, like, have a clarity on what formula I can apply. Look, every formula is applied in a particular scenario, in a particular condition under certain assumptions. So whenever you are writing a formula in your short notes, write in what condition you are going to apply. Okay, it's very important. People do a lot of mistakes. They will just randomly apply any formula anywhere. Okay, they are always confused where I can apply this. Please do not do that. Just try to be very clear about when you are going to use which formula. Okay, so I think we can stop here. Already we are 10 minutes late, but it's fine. Okay, but please revise. I think next class is today's what? I think next class is Friday, I think. Okay, so I'll meet you on Friday. Okay, good. I hope you were able to understand the topics. If not, I mean, if any doubt is there, please revise first. Okay, it's very important. Thermodynamics is a very confusing subject. I mean, you cannot do anything about that. ठीक है, चलो, let me quickly shut down the meeting, and then I'll see you on Friday. Goodbye. Okay, Hers, thank you. I'm happy that you were able to understand everything. ठीक है, okay, tata, bye bye. I'll see you on Friday.